In 2025, an unexpected event unfolded deep within one of Google's most advanced quantum research facilities. Hidden away behind layers of security and chilled to near absolute zero, an array of ultra-powerful quantum processors capable of running computations that would take classical supercomputers millions of years to solve were put to use for something extraordinary. But this wasn't about simulating molecular interactions or particle behaviors, the usual realm of quantum experiments. This time, the focus turned to something far more enigmatic, a machine drifting alone through the vast emptiness of space, over 15 billion miles from Earth in the cold darkness of interstellar space. Voyager 1, a spacecraft launched nearly half a century earlier, became the subject of a classified quantum simulation. It was no longer simply a question of how long it would last or when it would shut down. The simulation set out to model Voyager's final moments, capturing the decline of a probe that had long served as humanity's most distant representative. Its power, drawn from slowly decaying nuclear batteries, was dwindling, and the engineers expected to see a gradual system failure, a predictable fade into silence. But the outcome of the simulation caught them off guard. Instead of a routine shutdown or a sequence of technical malfunctions, the data revealed something deeply disturbing. The patterns it showed did not align with conventional expectations. Instead of random signal degradation, Voyager's data appeared to be following synchronized intervals, behaving as if the systems were entangled in a way that defied the classical physics the probe was built upon. According to two individuals familiar with the project, who spoke under strict anonymity, Voyager's communications showed unexpected correlations across time. This wasn't supposed to happen. The probe was isolated, drifting alone in deep space, far from any known object. Yet the signals hinted at a kind of interaction, as if Voyager was somehow responding to something out there. Researchers began asking unsettling questions. Was the probe encountering unknown forces or phenomena? Was something interacting with it, perhaps even observing it? The simulation suggested Voyager wasn't simply dying. It was behaving actively, adapting to something invisible, something unaccounted for. And then, just weeks after this unsettling, model circulated quietly within a small group of researchers, reality followed suit. In a twist that was more than coincidental, Voyager 1 suddenly began transmitting corrupted, nonsensical data. The actual probe experienced a data glitch, one that mirrored the very same pattern the simulation had forecasted. This wasn't just strange, it was chilling. Engineers at NASA's Jet Propulsion Laboratory were baffled. The probe's telemetry had turned into digital gibberish, seemingly out of nowhere. After a thorough investigation, the issue was traced to a corrupted portion of Voyager's flight data system memory. Somehow, after 47 years of stable performance, a vital segment failed, disrupting its communications. NASA offered a logical explanation: wear and tear from decades of exposure to cosmic radiation. But for those aware of the simulation, the timing was far too precise. The predicted glitch and the real-world event aligned almost perfectly. Some began to wonder, was this an accidental forecast, a statistical fluke, or had the simulation somehow caused the anomaly? It was a terrifying idea that modeling an event might influence its occurrence. The line between observing and altering had begun to blur, leaving scientists grappling with the possibility that their predictive tools were shaping reality, not just analyzing it. If these simulations could be refined and better understood, the implications for space systems engineering would be immense. We could foresee the failure of spacecraft years in advance, revolutionizing mission planning and diagnostics. But excitement quickly gave way to philosophical unease. In quantum mechanics, it's known that observation changes a system. Could the act of simulating Voyager's end have increased the likelihood of that very outcome? These were no longer theoretical debates. They were profound questions that touched on causality, consciousness, and the limits of what it means to observe. Was Voyager's fate always destined to play out this way, or had the simulation nudged it toward that path? If quantum systems can influence classical outcomes, even subtly, what does that say about our role as observers in a universe that might be more interactive than we ever imagined? Neither Google nor NASA acknowledged that any such simulation took place. When asked about quantum computing and space missions, their responses remained vague and general. Yet behind the scenes, insiders reported abrupt and unusual changes. Engineers associated with the simulation either resigned or were reassigned. Access to the quantum systems was revoked. Then came the most telling move, the complete deletion of all simulation data from Google's servers. Not archived, not secured, deleted. No technical explanation was provided. Team members were simply told this research was not to be continued. The message was clear. Someone, somewhere, had decided the knowledge gained from that simulation was too dangerous to exist. The speed and decisiveness of the purge raised serious concerns. What had the simulation really shown? What had made those in charge so uncomfortable? To make sense of this, one must understand how quantum simulations work. Unlike classical computers, which process information in bits, quantum systems manipulate quantum bits, qubits, that can represent multiple states simultaneously. This makes them especially suited to simulating complex quantum interactions, such as magnetism, exotic materials, or molecular structures. Google's Sycamore processor and its successor, the Willow chip, released in 2024, are at the forefront of this field. These machines excel in quantum domains, but they've also been used in hybrid models that combine classical data with quantum analysis. Such models have found surprising success in financial markets and climate science, fields where vast, interconnected systems produce emergent behavior. Voyager, while operating in a realm governed by classical physics, may have revealed unexpected correlations when viewed through such a lens. Voyager 1 and 2 were launched in 1977 for a brief mission to study Jupiter and Saturn. But they kept going, powered by nuclear batteries, and are now traveling beyond the heliosphere into true interstellar space. They send back weak signals across unimaginable distances, and engineers have worked tirelessly to conserve every ounce of power, shutting down instruments in phases to extend their life. A major shutdown is planned for around 2026. Whether the simulation was a fluke, a breakthrough in predictive modeling, or something more profound, one thing is clear. The boundaries between forecasting and influencing have begun to erode. We are entering an era where computers might not just simulate the future, they might affect it. If a quantum simulation can mirror a spacecraft's failure from 15 billion miles away, we are forced to confront unsettling questions about free will, probability, and even time. Voyager continues its lonely path, fading ever so slowly. Whether its recent malfunction was just a coincidence or a manifestation of something deeper may never be known. The data is gone. The researchers are scattered. The official story remains unremarkable. But beneath the surface, the implications are still echoing through the scientific world. Our tools are growing so powerful, they may be reshaping the very phenomena we aim to understand. And Voyager, our silent emissary to the stars, might have been the first to show us that, in our quest to model the cosmos, we may also be rewriting it.